Okay, so let's get started. Pratik, Rath, holographic duality of entanglement negativity.
Thank you. Thank you so much for the invitation. Yeah, thanks. So thanks a lot to the organizers for giving me a chance to give this talk. So this is some work that I've been doing with Shi Dong and Jonah Kudler-Flam, who's a postdoc at the IIS. We wrote one paper last year, and there's some more work to appear, which is basically what I'll talk about. So let me get started by giving you some quantum information background and motivation. Luckily, a lot of this was already talked about by Abhijit, so I can be brief about it. So we know that for bipartite pure states, all correlation that the two parties have is actually entanglement. There's a precise way to say this, which is that when you just have pure states and you have many copies of them, the amount of Bell pairs you need to make the state is pretty much the same as the amount of Bell pairs you can extract from the state, which is called the distillation. And both of them are measured by the entanglement entropy, or equivalently the mutual information. This stops being true once you have bipartite mixed states. And so in that case, there's a distinction between classical correlations and quantum entanglement. In particular, separable states are the ones which have only classical correlations. They can be generated just by having local operations on the two different parties, as well as some classical communication. So in particular, what a separable state looks like is like the follows. Rho AB takes the form sum over I, Pi, rho AI, tensor rho BI. So you sort of flip a coin, you get some outcome, send it to both the labs, they prepare some state. That sort of state is given by this. There's no entanglement, though those states can't be used to violate, for example, Bell inequalities. So good entanglement measures should somehow differentiate this sort of correlation from actual entanglement, which can be used to perform tasks. And so they should vanish on such separable states. And moreover, they should be monotonic, so monotonically decreasing under LOCC operations, LOCC being local operations and classical communication, since you can't create entanglement by just doing those operations. There are many such quantities known, but unfortunately, they're usually hard to compute. Most of them involve something like optimizing over all possible purifications and things like that. On the other hand, there are some easily computable not entanglement measures, but correlation measures like the mutual information, but then they end up capturing classical correlation. So they don't just capture the entanglement part of it. So that's where the hero of our story enters. Entanglement negativity is one such thing which is both computable and an entanglement measure. So in order to talk about the entanglement negativity, we can first talk about the partial transpose. Partial transpose acts on operators on the system AB as follows. So you have some operator in the basis IA, JB, KA, LB. And all we do is flip the indices on the bra and ket of B, just on B. So it's a partial transpose in that sense. Now, this is an operation that doesn't send density matrices to density matrices. It, however, does send Hermitian operators to Hermitian operators, while also preserving their trace. So it does have real eigenvalues, which I've labeled by lambda I t. However, those eigenvalues can be negative. They don't need to be positive, since this is not a density operator anymore. And in fact, it's easy to check that partial transpose leaves separable states invariant. And since to start with, they had a positive spectrum, the partial transpose preserves that. And so if you have separable states, they don't have any negative eigenvalues under this partial transpose. And in fact, that also implies that the presence of negative eigenvalues is somehow indicative of quantum entanglement. There's a precise version of this, but yeah, that's basically true. On the other hand, the converse is not true. So you can have things which don't end up getting negative eigenvalues under the partial transpose, but they still could be entangled. This is what's called bound entanglement. But anyway, but we're going to use this as an indicator of entanglement. So if we find states which have negative eigenvalues, then we can be sure that we have some amount of entanglement which can be used to perform tasks. Yeah, that's a good question. I know this has been analyzed, I don't know the answer to this. Maybe Jonathan or someone has an idea, do you know? How generic is it to have separable states versus negative partial transpose? So pretty much all states have negative partial transpose. Is there an expectation for it? Yeah, okay. Okay, good. So using this fact, it's natural to define a quantity called the entanglement or logarithmic negativity, which was defined by these people, which is basically log of the sum of absolute value of the eigenvalues. Obviously, if all of them were positive, since we know the trace is 1, this would just give you a 1 and log would be 0. So the entanglement negativity vanishes when you don't have negative eigenvalues. And obviously, this is more than 1 if you have some negative eigenvalues. And so that would indicate some presence of entanglement. Okay. So this is an operationally useful quantum information quantity. And more importantly, it's computable. So it's something that we can actually put on a computer and compute. So this is a useful way to characterize whether bipartite mixed states have entanglement or not. Okay, so that was the quantum information motivation for it. Since this is such a useful quantity in quantum information, it's natural to think about it in holography. In particular, over the last few years, or last decade or whatever, we've realized that entanglement plays some crucial role in the emergence of geometry in ADS-CFT. In particular, the gold standard for this is the entanglement entropy, which has a Ryu-Takayanagi formula, where you relate the entanglement entropy to some area on the bulk side. And so the goal here is, can we generalize that? Can we understand something like that for this quantity, which measures entanglement between bipartite mixed states? So for the entanglement negativity. There have actually, this problem has actually a long history, and there have been several proposals in the literature. Gautam has written papers about this, Shinsei Ryu and collaborators, Dong, Xiaoliang and Walter have written a paper. And all these proposals, the annoying thing is they don't all agree with each other. So there's distinct proposals and it wasn't really clear what the right proposal is. So this has remained an unsettled question for quite some time now. In fact, some of these papers were like almost 7-8 years back or so. Good. So the goal here is to present a proposal for the entanglement negativity, for the holographic dual of the entanglement negativity for general holographic states, and sort of prove it using the gravitational path integral, prove at the level of what we can say using the gravitational path integral. So the spoiler will be that it ends up disagreeing with the results in these two papers, and it only partially agrees with the results of this paper. So in fact, it's sort of a completely different proposal. On the other hand, it does agree with more precise calculations like these resolvent calculations in JT gravity models of black hole evaporation, like the PSSY model, which were done in these papers. So let me now delve into the history of the problem a little bit. So the CFT calculation is pretty straightforward to state. So for the purpose of this talk, I'll be mostly talking about two intervals in the vacuum state. The proposal is much more general than that, but let's focus on that just to understand the issues. So entanglement entropy can be computed for two intervals in the vacuum state, just as a 4-point function of twist operators. And this was done back in the day by Tom Hartman for large central charge theories. And the story is pretty simple. For the intervals being small, the vacuum in the S channel dominates, the vacuum exchange in this 4-point function dominates. And for x more than half, which is when the intervals are large, the vacuum exchange in the T channel dominates. This is very natural because the vacuum is the lowest operator there, and at large central charge, we expect it to dominate. And that's perfectly consistent with bulk calculations, which were done by Tom Faulkner, which is basically the RT formula. Right? So now we have a lot of evidence for this, and so this picture seems perfectly well understood. So the calculation for negativity is pretty similar. What it involves is computing even Renyi negativities. So you compute this quantity E2k, which is basically log of trace rho transpose to the 2k. The 2k is important because we want this absolute value. You start from 2k, and then in order to get the negativity, we want to analytically continue this to k equals a half. This was set up in the CFT side by Cardi, Calabrese, and Tony, shortly before these papers, actually. And so the natural guess is that you again just say the same story. In either of the phases, you just assume that the lowest operator that's exchanged in the 4-point function is the one that dominates, and you just get the dominant contribution from the conformal block corresponding to that operator being exchanged. On the bulk side, so in the disconnected phase, it's pretty straightforward. You just have a so notably, yeah.
Is there some issue of analytic continuation that ensures you don't get log of sum of lambda I and mod of lambda I?
Log of.
You could also have written that without the mod, right? And then you might have
this thing?
It, yeah. You might have valid as you did k equal to half, you get log of sum of lambda. So you start. I guess the answer is that. I mean, is there some subtlety in this analytic?
I think this. I mean, so I think you can basically apply like Carlson's or whatever to this form of it.
Not to the one without the mod.
Yeah, the one without the mod, but I think analytically you can do that, but I think you'll get a trivial answer, which is just you'll get the trace, which is 1, so you'll get 0. So that's a different analytic continuation. So in this case, so maybe one thing I can say is like there, what you do is you do it at all integers, right? So you have the odd moments and the even moments, and for the odd moments you'll have some sign, right? So depending on whether you do the mod or not. So those will be 2 different continuations, one of which will give you this, the mod, the other one which will give you just 1, like, yeah. I don't have to, but I think he's asking like, how do you do the analytic continuation? And I think there's like different ways. That's right. Yeah, this 4-point function just computes this. So I think he wants that, he's just talking about that piece. Yeah.
So you can't just the thing in the first bracket, if you continue, you expect to get 0. Not if you have 2. So with k at k to the half, k to the half.
I mean, I guess it depends on how you're doing the continuation. Are you including the odd moments as well or not? Like, I think the question is that.
Just think of this as a function of a natural number k.
Yeah.
That has an analytic continuation Carlson's theorem. You take that k to half, you get what you want.
That's right. But instead of having this 2k, if you had an n and you took the odd moments as well, then you'll get what you said. Okay. So again, there's 2 phases. So the important distinction between these 2 pictures is the orientation of the twist operators. So here we had twist, anti-twist, twist, anti-twist. Here instead, because of this partial transpose, we have twist, anti-twist, anti-twist, twist. So it just flips the orientation. And so in the disconnected phase, nothing significant happens, but in the connected phase, now we have a contraction between the twist operators and the anti-twist operators. So the vacuum can no more propagate in this 4-point function. And so the lowest operator is instead a double twist operator, which is reasonably well understood. If you make the same assumption that was made here, which is that this operator dominates, so you just include the contribution from the conformal block corresponding to this lowest operator, then you get something, get an answer both on this CFT side and on the bulk side. You can relate it to basically a back-reacted version of the entanglement cross-section. So you can imagine that this corresponds to the diagram for this 4-point function. And this bulk calculation basically follows from assuming full replica symmetry. So this thing, when we have 2k copies, has a Z2k replica symmetry, and by assuming that, you get this cross-section. Good. So that was all good for the CFT part. But there's an alternate calculation which was done in random tensor networks. So random tensor networks were briefly mentioned in Ronak's talk. And the idea is that, so you basically have these tensor network models where you pick, like you discretize the bulk, and you pick random tensors at each location, contract them in a particular way dictated by the geometry. And that defines a state. So tensor network prepares some boundary state where you can compute entropies. And the reason these are useful toy models of ADS-CFT is because the replica trick that you do for random tensor networks is very, very closely related to the replica trick you would do in gravity, as long as you use what are called fixed area states. So fixed area states are these states where instead of having, it's sort of the micro-canonical version of the state. So it's like where you restrict the fluctuations of the area to be much smaller than what would usually be the case in the vacuum state. And there's a completely bulk description of these states using the gravitational path integral. And you can check that the replica trick in the tensor network matches almost identically, including non-perturbative corrections, with the calculation in gravity using fixed area states. So let me describe the random tensor network calculation a little bit. The replica trick basically involves, so you take many copies of this tensor network, and they're all random tensors. So at the end, whatever you compute, you want to average over the random tensors. That averaging basically does something analogous to what Jan was talking about. It can correlate the different copies. And so the calculation ends up being something like an Ising partition function, where you sum over all the possible permutation elements at each tensor, subject to boundary conditions that are set by the quantity we are computing. So in particular, for the negativity, we want to apply the twist operator, which is a cycle at subregion A. Because of the transpose, we apply the inverse of the cycle at B, and the identity at C, which is what we're tracing out. So subject to those boundary conditions, you can look for saddles in this partition function. And the naive replica symmetric saddle takes the form basically of the entanglement wedge cross-section as proposed. So it looks like a domain of identities near C, a domain of this X, which is the cyclic permutation near A, and a domain of anti-cyclic permutation near B, which meets at a cross-section. And so the domain wall at the cross-section basically gives you this cross-section contribution to the negativity. However, in the tensor network, we understand the set of saddles much better. We can basically classify all of them using this permutation group. In particular, it turns out that there's a particular distance measure between permutations, which is called the Cayley distance, which dictates what the energy cost is of having different domains meeting. And under this distance measure, there happens to be a class of replica symmetry breaking permutations called tau, which lie precisely between these permutations. In particular, it has this funny property that it lies on the geodesic between X and X inverse and E and X. So it's on a common geodesic between all 3 points. And there's many such elements, all of which break replica symmetry. So if you have that sort of a permutation, you can just insert a small domain in between. Since it lies on all of the geodesics, this doesn't cost any energy. But now I can allow this domain to relax, and it leads to some sort of configuration of this sort where you have a tau domain in the middle. This is provably the right answer in the random tensor network. There's this class of permutations tau, and many of them, almost all of them break all replica symmetry. At best, they preserve a ZK symmetry. So remember that there was a Z2K replica symmetry initially, and the best you can do is preserve a ZK symmetry. In fact, in this paper, they looked at a slight deformation of this random tensor network. Random tensor networks typically have legs which are maximally entangled. You can consider versions which have non-maximal entanglement. And that sort of breaks this degeneracy between all the permutations. But there's particularly 2 of them which preserve this ZK symmetry that end up dominating. The dominant answer is given by some ZK symmetric classical saddle. So this is pretty suggestive, and then you can ask whether the same happens in gravity. So that's what we were after, because this sort of already gives you evidence that the answer in fixed area states is given by a saddle of this form, which breaks some of the replica symmetry. And so you can ask if that happens also in more general states, like for example, the vacuum state. Okay, so in order to prove this, there was one simple idea, which was an identity relating the partial transpose to what we call the double state. So there's a very useful identity which says rho transpose squared is basically the reduced density matrix in the state rho AB. So we're pretty familiar with the canonical purification. Tom talked about it last week, and that's the state square root rho, which is the natural thing we consider in the thermofield double. This instead is the state rho. So it's not literally a purification, but it's some other state you can consider where you just take the density matrix rho and flip all the bras to kets. That gives you a state on 2 copies of the system. So that gives you a state on AB and A star B star. In that state, you can consider the density matrix and look at the reduced density matrix on the system A B star. As an identity, these are related. Yeah. So there's an initial system A, B, C, let's say. And then we reduce the density matrix to AB. So that's a mixed state. Now we do this doubling, which gives you a state on AB and another copy, which is A star B star. It's a pure state. It's not a purification of the original state because you don't have the square root, but it's still a pure state. And in that pure state, you can look at the reduced density matrix on AB star and compute its, that matches this rho transpose squared. Yeah. So the state itself may not be basis independent. I think you have to choose some anti-unitary for this thing, but in the end, the entropies will end up, this is similar to the reflected entropy. You have to worry about the same thing in the reflected entropy. The entropies end up being independent as long as you use a transpose which respects locality. There's some ambiguity in that, but the entropies don't care about that. So there's a simple pictorial proof of this. It's like a very trivial identity, actually. So we first have the density matrix rho AB, which has 4 legs. The transpose just flips the legs on B. And the square is just matrix multiplication. So you have this picture. Now the state rho AB is obtained from this operator by just flipping all the bras to kets. So we get a state which lives on 2 copies now, AB and A star B star. The ket is similarly rho star with all the legs turned around. By using hermiticity, we can basically replace rho star with rho as long as we replace the AB legs with A star B star. And so that gives us this picture for the density matrix, for the full density matrix on this double state. And then we finally trace out the system's AB star. That picture looks like this. By straightening this leg, you can see that it's the same as the top picture. It's a very straightforward identity, but it's very useful. And the reason it's useful is because what we were interested in computing for the negativity was the 2kth moment of the transpose density matrix. And so now all I need to do is compute the kth moments of some density matrix in a state, which is this double state, which itself is well understood. This rho AB state has been well understood in the context of understanding the reflected entropy. So then all I need to do is compute some Renyi entropy, which is much better understood. Okay. So let me describe what this double state looks like. This double state is obtained basically by cutting open the saddle that computes rho AB. So that's the usual thing where we just look at the norm of the state. There's some geometry computing that. But equivalently, as Tom described in his lectures last week, the norm is basically just trace of rho AB dagger rho AB, which is the same as trace rho AB squared. So this is just computing the second Renyi entropy of the system AB in the original state. So obviously, because we're computing a second Renyi entropy, there's some back reaction. But nevertheless, we understand what this is like. But the answer that we'll get for the negativity will not be a probe-like quantity like the RT formula, which is just something evaluated on the same geometry. This will have some back reaction. So for the 2 intervals example, let's see what the double state looks like. So trace rho AB squared for 2 intervals is just computed by the torus partition function. It's like a well-known thing in the CFT literature. And we know what the bulk dual for the torus partition function is. There's 2 saddles, depending on which phase you're in. There's the BTZ saddle and the thermal ADS saddle. In this case, yeah. It's the vacuum. So in this whole talk, I'm only going to talk about the vacuum 2 intervals. 2 intervals in the vacuum state.
2 intervals being A, B, and the rest being something.
Yes. All of this will go through nevertheless, but to highlight, to illustrate, I'm just going to talk about this example. So here, so in particular, the torus partition function computes the trace rho squared for that 2 intervals in the vacuum state. In the connected phase, we basically have the BTZ saddle. And what we're instructed to do is just cut open the state in the middle and look at what the state looks like. So we cut open the BTZ saddle in the middle. So that gives you this Cauchy slice, which is this red slice. The C regions have now been traced over, so we just have a system which is living on A, B, A star, B star. And what it looks like is the following. So there's two circles. There's a circle A, A star, and there's a circle B, B star. This basically looks somewhat like a two-sided black hole. I mean, it's not precisely like the thermofield double, but it's some back-reacted version of that. So, so now we have two asymptotic boundaries with these this sort of cylinder connecting it. And now all we have to do is, in order to compute the negativity, we have to just compute the entropy of subregion A, B star in this saddle, which is pretty straightforward. So let's do that. At integer k, we assume, it's pretty standard to assume ZK replica symmetry for the Renyi entropy. There's sufficient evidence by now for that fact, but obviously I'm going to assume that in order to make any progress. And what we normally do is look at ZK symmetric solutions and then quotient by that to obtain cosmic branes, which are these conical defects. What do they look like? So in this torus, but there's different possible configurations for the cosmic branes. And since we're looking at A, B star, so one choice is this green, solid green surface. Basically this one union this one. This is something, it's basically the disconnected solution in this geometry for the branes. And it's homologous to AB star. And obviously, so the full replica symmetry of the original problem is reflected in the fact that there was a Z2 symmetry in the doubled state. There's a Z2 symmetry under exchanging AB with A star, B star, which is basically across this horizontal line. And clearly, this solution breaks that symmetry. So since it breaks that symmetry, its Z2 image, which is the dotted line, is another possible candidate for this Renyi entropy. So there's two of them, and they're precisely equal to each other. So it's right at the phase transition. But nevertheless, we know that that's the dominant solution in this case. In particular, the Z2 symmetric saddle would have looked something like this. It involves the original entanglement wedge, so the RT surface for the system AB, plus something that looks like the cross section. You can think of this as being homologous to AB star by thinking of it as a limit of this surface where we go halfway, go around, and then go halfway here, plus halfway, all the way around and halfway. So that would be, it's sort of a limiting case of an RT surface. But obviously, we know that by smoothing the corners, you get something that has lesser area. So this couldn't be the dominant solution. Yeah. No, right now I'm just drawing the pictures at integer k. Yes, yes. So this picture is heuristic in that sense. I don't mean that it's literally the same geometry that we had in the last picture. It will be when we go, so we can analytically continue and go to k equals 1, not half. That's when these become probe. Because it's computing the kth Renyi entropy. So the entanglement entropy limit of it is not the negativity limit, but it's some other limit where they will become probe, and then you can think about the same geometry. But in general, this is just a heuristic picture. Like there will be some back reaction, the geometry gets deformed, but nevertheless, the topology will be this. Any other questions? Okay. So good. So the Z2 symmetry, which was is precisely broken in the sense that the RTN calculation predicted, and you can in fact show that this this blue saddle is not even a saddle. It cannot ever descend from the quotient of a smooth parent spacetime. This is very closely related to what Abhijit was talking about yesterday. It has to do with the intersection of the brain. It's a special case of that. So now we can analytically continue. So this was at integer k, where we understand the replica symmetry is broken. Yeah. Yeah. Yes, yes, yes.
Is there some appearance of tau?
So tau, so if you wanted to secretly think about this as like, if you open this up, the permutation, the pattern of gluing will basically be exactly of the form of tau. There is back reaction in this case, so it's not literally that. But the gluing pattern, which is dictating the topology, is exactly the same as tau.
Gluing pattern on the boundary?
No, in the bulk. So imagine these were fixed area states. Then I could just literally take copies of this system and glue them together, and then it would be exactly tau. But in this case, because of back reaction, it changes a little bit. But the topologically is the same. And the fact that, because there was a Z2 symmetry breaking, there were two such tau, and those two such tau correspond to the two different surfaces. Okay, so now we can analytically continue in K, and that would be sufficient to compute the Renyi negativities. But there's a problem because this only actually ends up working for K greater than 1. And so at least for K greater than 1, this is basically a proof from the gravitational path integral of the proposal that was made by Dong, Chi, and Walter. So now let me say what's the problem for K less than 1. For K less than 1, there are actually by now sufficient evidence of the fact that this cosmic brane proposal, where you just add this brane, can actually have leading order corrections, so order 1 over G corrections compared to the actual answer in the CFT. This has been computed, for example, in the PSSY model in these papers, and also in the condensed matter literature, there's some version where these people computed it for high energy eigenstates, and if you translate all of that to holography, you find that again, there's large corrections when you compute the Renyi entropy for n less than 1. So you need some new proposal to compute, and by the way, this only happens, as far as we know, when you have multiple candidate extremal surfaces. So you want some two surfaces which exchange dominance and so on. But here we're precisely there, because in the negativity problem, we're right at the phase transition. So this is exactly where this proposal is important. So we need some new proposal. And just to briefly mention this, the base K more than 1, minimality of the RT surface is sort of automatic, because the action that's computed by Lukowitz-Maldacena goes like e to the minus K minus 1 area over 4G, where area is the area of the surface you're replicating about. So since K is more than 1, minimizing the action just automatically minimizes the area. For K less than 1, this actually doesn't work, and it's not quite clear how to continue it. And in particular, you can again take the help of fixed area states, where we understand it because we understand random tensor networks. And there the rule is basically that no matter whether you're at K greater than or less than 1, you just pick the minimal area surface. Nothing funny happens at K equals 1 in that sense. So it suggests that the minimality of the cosmic brane is crucial, and somehow that should be incorporated in the proposal, which doesn't automatically happen in the cosmic brane proposal. And in particular, the issue is for K less than 1, the cosmic brane has a negative tension. Negative tension branes will tend to increase the area of the surface. And so in the negativity problem, what you can do is you have these two surfaces, you put a negative tension brane on one of the surfaces, it increases the area, so now you're replicating about not the minimal surface, because the other one now has lower area, and you can do the opposite and put the brane on the other end, but because of Z2 symmetry, the same thing happens. So neither of these saddles actually computes the right answer. So you need some new proposal. So this is basically what we did in the the paper from last year, which was just a proposal for the Renyi entropy for n less than 1. Yes. Yes. From n less than 1. Yeah.
From below n.
Yeah.
Onwards, right?
Yeah. Yeah.
What you said.
Yeah, it's a good question. I've thought about this, but the issue is, so normally all of those calculations are in this U1 symmetric case where it's the black hole, and there's only one candidate surface in that case. So it's not obvious that there's any issue. Like for example, for the single interval vacuum entropy, we have some universal form, right? It's just fixed by conformal symmetry. And surely that's right. Like I don't think there's anything wrong with that. And the reason is because there's not multiple candidate surfaces that are there to compete. So this is only relevant when you have multiple candidate surfaces, which is generic, but so I think those calculations might get away because of that. Yeah. You can, but it's just very hard. Like doing it analytically is just a nightmare. Yeah, so this is something which is supposed to be something that, like, you know, if you at least in principle, have some semi-classical proposal where you don't have to actually sum over all possible geometries and stuff. That would be very hard. You can do it in JT gravity, and this result will end up agreeing with the results obtained there using those methods, but this is more general than that. It's sort of inspired by that. Yeah, okay, good. So let me just very briefly mention the proposal. Let me just go over the idea. I won't be able to go through the details, but the idea is, since we understand fixed area states reasonably well in terms of this analytic continuation, we can decompose any general state in this basis of fixed area states. We'll have some amplitudes times the fixed areas where we have area A1 on surface 1 and A2 on surface 2, where these two are the candidate RT surfaces. The amplitudes here, the probability distribution P of A1, A2, can actually be computed using the path integral. This was done in these papers. And there's a very explicit bulk way of computing the probability distribution over areas. Essentially what you do is you compute, so psi would have been the boundary conditions at infinity that you would impose to compute the norm of this state. But in addition, you add a projector onto areas. So that means imposing a boundary condition of fixed areas at these two locations with some definite values. Those saddles would have conical defects, but nevertheless, that's the boundary condition you're imposing, so they're the solutions consistent with that. And essentially normalized by the true norm. So what that gives you is the probability distribution is exponential of the action of the smooth saddle, which is the usual saddle we'd compute, minus the action of this fixed area saddle. That's some very explicit bulk way in which you can compute this probability distribution. So it's not just some abstract number. Yes. Yeah. Yeah, they have conical defects, yeah. Yes. Yes, yes. I mean, this is similar to writing coherent states in the basis of eigenstates. Morally that. Right. So you can make it. Yeah, I agree, but I mean, I think morally it's the same as the statement that, yeah, it's just some basis, right? So, but okay, so when I say it's this, so this fixed area, I mean, there's a lot of freedom in what we mean by this fixed area. We don't literally mean an eigenstate of the area. We mean something like the microcanonical window where those fluctuations that you're talking about are sort of smoothed over, similar to your kernel. So you have some sharply peaked, like much more sharply peaked than usual states, but something which is sharply peaked so that it has a flattish Renyi spectrum, but nevertheless, it doesn't like see the distinction between microstates. So it's sort of in between them. So it's slightly smoother than that. Okay, so given this, so this description of the state, we can just literally take this, compute the reduced density matrix. We get some terms which are basically diagonal, which have the probability weights times the density matrix you would obtain in the state, in the fixed area state, plus some off-diagonal contributions. Now, if we, as Lukowitz and Maldacena suggested, at integer k, we could try to just keep replica symmetric terms. So if you look at all the different terms that you'd get when you compute trace row to the k, there'll be many terms which have different, because of these off-diagonal terms, you can have different values of the area coupling with each other. Those would give you geometries, which are fixed area geometries, but nevertheless replica symmetry breaking. So if we want to go with just the replica symmetric ones, then we just end up with keeping the diagonal piece, which is a maximization over all areas, p to the k, trace row to the k, for the fixed area state. This perhaps can be justified better, and this is some work in progress, but I won't say much about that right now. What I'll say is that this proposal ends up agreeing with all the calculations we have in the literature. So there's sufficient evidence for it. Okay, so once we have that, we know trace row to the k for fixed area states. We know how to analytically continue that even past k equals 1. And so we get some proposal. The proposal looks as follows. So we have an optimization of a function. This function should be thought of as minus the action of the fixed area saddle. where you have replicated about the surface I. So there's a label I which dictates which surface about which you're doing this replication. So there's two optimizations. There's a maximization over the surface that's basically imposing the minimality constraint. And then you maximize over all possible saddles given that. The interesting thing that happens for k less than 1 is that because of this 1 minus k, this maximization changes to a minimization. And that makes all the difference. So there's a way of reformulating the cosmic brane proposal in precisely these terms, except the order, except the order of optimization is the reverse. So for k more than 1, that doesn't matter because two maximizations always commute with each other. But for k less than 1, max min is not the same as min max. And so that's why this proposal is different from the cosmic brane proposal for k less than 1. And this ends up agreeing with calculations done using, say, the resolvent and so on. So that's the updated version of the Renyi entropy proposal. Okay. Yeah, I'm almost done. So finally, we can put all of that together. We realized that we could relate the entanglement negativity to some Renyi entropy, the half Renyi entropy in this double state. So we can compute it using our proposal. And there's some normalization factor which gives rise to this minus half second Renyi entropy of rho AB. But apart from that, we get this term from our modified cosmic brane proposal. There's a max min because it's for k less than 1. And this P2 is the probability distribution of the areas in the double state. Of course, we're computing entropies in the double state, so we're just looking at that area distribution, again, which can be computed using the path integral. Once you have this, then you're just optimizing this function. This is basically just an optimization over some class of saddles. You look for the best saddle among them, that gives you this answer. We can check a simple case of this, which is for the fixed area states. So for fixed area states, these probabilities will be sharply peaked, and they'll be only supported at a given particular value of the areas. And also, since the double state itself was generated from a fixed area state, the areas themselves are just given by entropies in the original state. So this is in the state psi that we started from. The areas are just given by 4g times SA plus SB in the original state, which is basically the sum of this surface and this surface. The Renyi spectrum of rho AB was flat, so the second Renyi entropy of AB is the same as the entropy. So we have minus half entropy of AB plus half entropy of A plus entropy of B, which is half the mutual information. And this is precisely the proposal that Dong, Chi, and Walter had for random tensor networks. So that's a sanity check of our proposal. But in particular, in general, what will happen is this distribution will have some non-trivial spectrum. And often it can happen that the optimization of this can land you somewhere along the diagonal. So diagonal in the sense of if we plot the distribution as a function of A1 and A2, one of the candidate saddles is just moving along A1 equals A2. Which in effect says that, this modified cosmic brane proposal in that context takes a simple form, which is instead of putting a tension K brane at one of the surfaces, you put a half tension brane at one surface and a half tension brane at the other surface. You basically distribute the tension over these two. So it takes a nice picture of that form. Of course, that's something that's challenging to compute just because there's back reaction, but it's some concrete proposal for semi-classical states. So in the last few minutes, let me just go back to the CFT calculation and ask about what went wrong there. This is something that we don't understand very well from the CFT side because it's also hard to compute things, but the mistake must have been in picking this single conformal block corresponding to this lowest operator. Of course, that should become true in the OPE limit. In the OPE limit, in the strict OPE limit, there's only one operator that should contribute, which is the lowest operator. And that's true. So this proposal does agree, the CFT calculation does agree with our proposal in that limit. Nevertheless, the bulk solution is actually still replica symmetry breaking. So in this adjacent intervals limit, which is the OPE limit, you have these two intervals which are now adjacent. And our proposal looks basically of this form, where there's some domain of, so there's some replica symmetry breaking domain in the middle. The cross section would have been something like a surface going through the middle, which would be replica symmetric. The difference between these two solutions is actually a constant, and that constant is fixed exactly by including the contribution of the OPE coefficient. That was something that was ignored in a lot of these calculations. So it's perfectly consistent, and so what ends up happening is in strict adjacent intervals limit, the CFT calculation is dominated by this single block, and it's consistent with our proposal. But as soon as you go away from x equals 0 or 1, whatever like is the strict OPE limit, there's some other contributions that become important. Yeah. Yeah, that's what that was the basis of the original CFT calculation. I mean, in large C, you might expect that to happen. It's not clear what exactly, why exactly this is happening. Presumably, I mean, so something similar would happen in the Renyi entropy calculation if you went beyond x equals half, right? So you have these contributions from heavy operators becoming important, those OP coefficients are important. Here, somehow it's just happening immediately, and that's a little puzzling. Like somehow the radius of convergence is going to 0 in this strict large central charge limit. Yeah.
The difference is not just constant.
No, it's not. The function changes as a function of the cross ratio. Yeah. And so we've also checked this from the CFT side in the probe limit, which was this k goes to 1 limit, and you can show that our saddle dominates over this proposal. So it's interesting. I mean, I don't perfectly understand this from the CFT side. It would be nice if we can say something more concrete than this, but this is my understanding so far. And there's also a similar calculation for the PETS Renyi mutual information, which is the Renyi version of the mutual information, where you can see that you make the same assumption. You make the assumption that the lowest operator dominates, analytically continue, and you see that it's a manifestly wrong answer. Like it just doesn't continue to the mutual information. So maybe it's a generic phenomenon when you have these replica symmetry breaking solutions. Okay, so let me just summarize. So I gave you an explicit proposal for entanglement negativity in holography. The idea was to relate Renyi negativity to Renyi entropy in this double state. We showed that the full replica symmetry is broken down to zk. Then you can analytically continue, but to continue to k equals a half, you need this new cosmic brane proposal. And so it would be nice to understand this from the CFT and also understand the QI implications of our proposal. For example, in this paper, they talked about how CFT states can have, how holographic states can have bound entanglement. So with that, thank you.
Questions?
Yeah, sure.
So are there examples where these probability distributions PA1, A2 have been worked out other than fixed area states?
Wait, what do you mean? Other than fixed area states. There are some examples, but they're pretty simple. So yeah, it's only been worked out in like single interval examples where there's no A1, A2, there's just A1.
Okay.
That has been done.
But for which geometries?
For the vacuum, or you can do it for the BTZ black hole and so on, like that can be done.
Okay.
Basically situations where you have like a simple modular Hamiltonian, those have been done. The other ones, I don't know of any example where it's been done. PSSY is another example where it's been done. But, yeah.
More questions?
Yeah.
I'm interested in the future work points. So do you have any comments on this bound entanglements at this point?
You should probably ask Shreya about it. She's the one who's thought about it more. I don't. So in particular, let me just briefly say what they had done. So in their situation, they could compute the mutual information and the negativity using this resolvent trick. And they found situations where the negativity was already large, but the mutual information was close to 0. That's actually maybe quite a general thing, because here what happens is the phase transition for the negativity is determined by the second Renyi entropy, whereas the phase transition for the mutual information is determined by the entanglement entropy. And generally, those two can be very different. So there would be phases where the entanglement negativity can be large, but the mutual information is small. The entanglement negativity lower bounds the entanglement cost, and the mutual information upper bounds the entanglement distillation. So in that situation, you can be sure that it's a state which costs a lot of entanglement, but you can't remove any entanglement from it. So that's why it's bound. I don't know the generality in which we can make these statements, but presumably this is useful for that.
Oh yeah. So for the case of fixed area, if you compare fixed area calculation to the usual gravitational calculation, is there any case where these results are drastically different? Like for fixed area state, it gives it like a 0 or the 1, and while this gravitational calculation gives it order 1 or 2.
It depends on the question. I mean, since you're when you say the gravity calculation, you mean like for a smooth state, which is not a fixed area state? Yeah. Because those are just different states on the boundary, any quantity which is not continuous enough. So one thing you can say is like, so you can approximate a smooth state by a fixed area state. Like usually these states are sharply peaked. So like, for example, if you had a coherent state peaked at some value of x and p, you can find something which is narrower than that, but still peaked at some value of x. So you could compute things which would be consistent, but if it's not continuous enough, like the Renyi entropies, they'll be very different. So the Renyi entropies, for example, for fixed area states have this flat spectrum, whereas for other states, they have some non-trivial n spectrum. So almost any quantity like that will have large fluctuations, like large distinctions between these two. On the other hand, operator, like correlation functions, perhaps can be same because you can make these close and trace distance, and then the correlation functions would be similar. So correlation functions may not see the distinction between these two. Gautam.
Yeah. So if I understand correctly, what you're saying is that for the disjoint intervals, when they're in, I mean, there are CFT calculations for the disjoint interval in proximity.
Yes.
But this proposal, what you compute from this proposal is not matching with that?
So it depends on what you mean. So in this limit, in the strict limit, it agrees. Like
that's the adjacent limit, right?
In the adjacent limit. So in the strict adjacent limit, it'll agree up to the OP coefficient. If you compute the OP coefficient, it'll agree exactly. So there's no problem with that. But as soon as you go away from that limit.
Yeah, but then when you go away, there's a heavy operator exchange, right?
Yeah, I think there's some
that's the problem that you suspect.
Yeah.
Okay. We'll talk more.
Yeah,
about
sure.
It. Thank you.
Okay, let's proceed to the next one. Let's thank the speaker again.
Thank you.